Hello, welcome back. So in the previous video, we made the case that we are going to need, or we not in the future, right now, we need a new formulation that is more general purpose than the relative motion analysis using translating frames. And that new kind of formulation is based on the notion of a rotating frame. So here is the general setup. We have a base frame, let's call it capital XY frame. And we have a body that is rotating with some angular velocity omega. Note that I'm using capital letter here. The reason will be clear soon. Before we were using lowercase omega for rotation. It is capital letter. And I have a point B on the body, but let's, for the sake of generality, assume that point B can move around the body wherever it wants to go. So completely arbitrary setup for A and B, but B in particular. And we want to do the same thing. We know the motion of A, we know the rotation of the body. We want to find motion of B. Obviously, in this case, we need to have some information about how B is moving on the body. So let's add to the mix too. So what we are going to do, we are going to create a local frame. Let's call it little x, little y. And this local frame is fixed to the body and it is rotating with the body. So as the body rotates with angular velocity omega, it also, the frame also moves with the same angular velocity omega. And here is the first thing I want to emphasize here, is that just a matter of notation. We used to work with omega. Let me change color. This is convention. We used to work with omega to describe angular velocity of a body. But whenever we use the capital omega, we describe angular velocity of a frame. This is just a pure matter of notation. They're both angular velocities. But to distinguish and make the formulation easy to distinguish from each other, we use different letters so we know what we're dealing with. So whenever you see capital omega, it is convention that it is the angular velocity of a frame rather than a body. But as we fix our frame to a body, obviously they're going to be the same. One little side note here is that our formulation, what do I call it? Rotating frame formulation. Rotating frame formulas do not even need to depend on any body. Do not need, or do not, what how do I write it? Do not, they don't need a body. Do not need a body. Even if you don't have a body to have an angular velocity, you can still use this rotating frame and describe capital omega to the rotation of the frame and do a lot of interesting stuff with it. This formulation is completely general purpose. It works for any situation, whether you have rigid bodies, connected rigid bodies, just random points moving around in space. This formulation works. Okay, so going back to where we were describing the setup. So now I have a local frame, little xy, a base frame, big xy, and I want to relate motion of B to the known information about this moving and rotating frame. So position is easy. That's why I start with position. Let's say we know this, R of A. I'm running out of colors. We have some information about relative motion of B relative to A, R of B relative to A. And we want to find which color. Let's go with green again. And I want to find R of B. So position is easy. We know R of B equals R of A plus R of B relative to A. This is always the case. Doesn't matter your frame is only translating or translating and rotating or in any other situation. This always works. So that is your position. If you know this, you can find that. However, there is one little point that I want to mention here. Is let's go back to, let's take a quick detour here to translating frame. Before we had the base frame and the little frame, and the little frame was always parallel and remained parallel. So I had this xy, little xy. So in that case, little coordinate vector I was always parallel to, well, some base value, and j was always the same as the unit vector of your base value. So really, we didn't care about working with coordinate or unit vectors of the local frame or the global frame because they were the same. But now, when we are dealing with rotating frame, in rotating frame, this is your big I, big J, but now your little I, little j are turning, and they are not the same anymore. I is not the same as I, j is not the same as j. They change. So why is it important? Because remember, this equation is a general vector equation. However, for all practical reasons, you need to write these equations in terms of some numbers. And those numbers are usually the coefficients of the vector along your coordinate frame. And here you have a choice. And that is an important one. You can either write all vectors in ijk using the coefficient of these vectors along your base frame, or you can write them in ijk, little ones. Let me change my k. So it is a little one. Write all vectors in ijk. And be careful, do not mix them up. Because if you do, obviously all your equation will fail. But sometimes it is easier to start with one frame, but eventually converge everything to the same frame. And in that case, for instance, let's note here, let me draw this. This is, let's call it big J, big I, and your little I, little j, although both of them must be same size. Wait a second. So this is little I, this is little j. What you can do, if you have rotated some amount, you can find the coordinates, the coefficients of your little I and little j in terms of the other frame. For instance, you can write I itself is 1 cosine of theta big I plus 1 sine of theta big J. And this is how you can convert from one frame to another. Similarly, you can write about J. J, what is it? J is 1 sine of theta minus 1 sine of theta I plus 1 cosine of theta J. And when you are in planar, the two k's remain the same. So little k equals big K in planar motion, because you're not rotating out of plane. Okay, so this is very important. Although the equation looks rather trivial, you need to be careful in what coordinate frame you are writing these equations. So that is what I wanted to say about position. Next stop is velocity. So I'll see you there.